whether 0 vector belongs to the set S, and so I'm considering let S is a subset of the vector space V, where vector space V is the vector space over F. Okay, so I'm considering this set S. Now S will be a subset if and only if 0, so I don't need whether here. So 0 belongs to S, right? Then 2, for every x comma y, these towards the vectors belongs to S, it implies that x plus y also belong to S. And the third condition is for every c belong to F, it implies that c times the vector x belongs to S. These three conditions has to satisfy so that the set S is a subspace of the original vector space V. Yeah.
If it is subspace of a vector space,
Yeah.
then do we reduce the field or do we keep the field unchanged?
No. We keep the field unchanged because if you change the field, then probably it is not going to be a vector space. And
Like
we are
so,
considering,
like
yeah,
say if I have a complex plane,
Yeah.
vector space, then I take real space.
that is not the subspace of that vector space.
Okay, like
So-
I'm taking subset, right? I'm taking
Yeah. So let me give you an example. So if you consider C, this is a vector space,
Yeah.
but this is a vector space over which field?
Okay, it's complex.
It is also a vector space over the real field, right? So if you consider C to be a vector space over C, then you are asking if R, that is a subset of this vector space C, is it a vector space subspace or not, right?
Yeah.
So you have to consider then the original vector space C over the field R, because if you don't consider R, then there is a problem. If you take R as a subspace of this vector space, and if you consider the field is the complex number C, then if you multiply, so 2 belongs to real number, right? And if you multiply I with 2, sorry, I times 2, this is equals to 2i, but this is not belong to R, right? That means if you consider,
It's not a subspace in that case.
yeah, so to consider R to be a subspace of the vector space, sorry, C, you have to consider the field is the real number, right? Then it is a subspace of the complex number, subvector space of the original vector space C. Okay.
If you consider R, then it is a subspace.
Yeah.
But if you consider C, it is not a subspace.
So, and finally, we also proved a theorem in the last class that, let me state the theorem again. Theorem: a non-empty subset W of V is a subspace of V if and only if for each pair u comma v vector belongs to W and each scalar C belongs to the field if the vector Cu plus V also belong to W. So this is the condition that has to satisfy so that this W is a subspace, right? And you can check that it's these three condition is actually you can generate all these three conditions from this equation, right? Okay. Yeah.
During this things in the last class,
Yeah.
you were recapping.
Yes. He missed the last class and asked it. Okay. So today now let me start with the definition. Let S be a set of vectors in a vector space V over F. The subspace spanned by S is defined to be the intersection W of all subspaces of V which contains S. Fine. S is a finite set of vectors U2 vector UN vector we shall simply call W the subspace span by the vectors vector. So this is the definition of the span. So
we have finite set.
yeah, no, in general not because we can consider the polynomial and then the set would be infinite set. But for a finite dimensional vector space, it has to be finite. So, yeah, I will prove a theorem on that. So, are you okay with it? Yeah. So now let me state. So for spanning, we have to consider that this is important here. Span by S is defined to be the intersection W of all subspaces of V which contains S. So we are going to consider all those subspaces which contains the set S, and if you take the intersection of all those subspaces, you get the
So this is
Yeah.
common to all. This S is common to all.
yeah, S set has to be in all those subspaces. Okay. So now let me. So there is a theorem. The subspace spanned by a non-empty subset.
Excuse me.
Yeah.
Sorry, just very difficulty for me. So you stated the theorem first, right?
No.
Non-empty
That is the
subset.
definition.
No. On top of that, there is a theorem. Also.
Okay, yeah.
There is a theorem. So you are trying to prove this theorem?
No.
Oh,
This was the theorem I proved in
Oh,
previous
okay.
class.
So these are already proven.
Yeah. The subset spanned by a non-empty subset is of a vector space V is the set of all linear combinations of vectors in S. So this theorem says that the subspace spanned by a non-empty subset is that subspace will be the set of all linear combinations of vectors in S. Okay, so the if you consider S to be a set like U1 vector, U2 vector, Un vector, then the subspace spanned by this set is, and let us consider that that subspace is the subspace W. Then if you consider an element of this set V, then V can be written as V equals to some
I have
C1.
a question.
Yeah.
But why does the subset S have to be finite?
For the spanning, it is not actually.
I don't want them linearly independent. I can take infinitely many vectors. And I want the span of those vectors. Now, why do you choose S to be finite? Okay, leave this
Yeah,
question
so-
aside.
Okay, there is a problem with the convergence issue, if I recall.
Is it how it's done in Hoffman codes?
Yeah, because so then again the question arises like what he asked in the previous class. If I take like all the
No convergence questions arise. I take infinitely many vectors from the vector space,
okay,
and that forms a subset.
yeah,
I don't want them to be linearly independent or anything like that. I can choose, and
Yeah.
I can call for the span
Yeah.
of that set.
yeah, and
How is it violated? Why do I need to? Because you see that even if we have this to be an infinite set, we have all linear combination of vectors. Because when I am talking about linear combination, of course I am taking finitely many of them from the infinite set.
Yeah.
And I can still have everything satisfied.
Yeah.
So
And
you don't have to answer it right away. But that's just
Yeah.
the concept.
I think okay, so there is a problem. I think I will consider in a few minutes. Okay, so C1 U1 plus C2 U2 plus Cn Un. So you can write all these vectors as a linear combination of these elements of this set S. Okay. So now let us prove this theorem. To prove this theorem, let us consider let W be the subspace spanned by S. So if W is the subspace spanned by S, then each vector V,
Excuse me.
yeah,
What is the definition of vector span? Is it the length and stuff?
No.
Span, what is a span?
okay, so I defined it in here, right? Let S be a set of vectors in a vector space V over
there
A.
is a definition
Yeah,
of span.
yeah. So that is the way I define span.
Okay, so that is span.
So you can define it differently.
Fine, then just
I
there
think,
is a span.
I think you are taking an X, for example, X to be finite.
In this case, yes.
In this case, you are taking X to be finite.
Yeah.
And be finite, like say for in 2 dimensions, say in 2D, we just take an arc, Vs.
Okay.
Then we can span actually the entire vector space, which the entire vector space itself could be a subspace of the original vector space, right?
Yeah, but the idea is what Sar is asking: if you take infinite number of vector space from the vector
in that
space.
arc, there are infinite numbers of vectors.
I don't get your question.
Like say if you consider a two-dimensional grid and
Okay.
we take an arc,
Okay.
that we take that arc to be S, then we can linear span that, and we can have the entire vector space, right? And we can consider that the entire vector space is a subset of the original vector space, right?
But you can also take
It
like
maybe not a subset, but it is a subset.
yeah, but you can also take the subspace
So
0, comma x.
There are infinite number of elements in S because every point on that arc is it.
What do you mean by arc?
Circular arc, any curve.
How is this? No,
No.
if you have an arc, then how do you? So that is a subset of R2. You are saying,
Yeah.
and then you are forming. That is not a vector subspace. That's
Yeah.
right. But now you want to form a vector subspace.
Yeah.
Taking more possibility and
Yeah.
I don't see how it looks like after taking more possibility and combinations. It has to be a vector subspace at that end.
Yeah.
Yeah, so it is not immediate geometrically how it looks like after taking more possibility. So you are right that the subset that we are choosing does not have to have a vector space structure.
Yeah.
That can be any subset.
Yeah.
But the point is that the subset that you are choosing may fail to be a vector space. But now we want to construct a vector space out of those vectors from the set that we see. And we are defining the span to be the smallest subspace that contains all those vectors of the subset. And that is the reason we take the intersection of those subspace. That is the smallest vector space that contains that
set S.
Set S. So it is the way of constructing the minimal vector space containing that subset. But my question was if that subset can be an infinite set. Suppose R2 is the vector space that you start. And now on the real line you have the set Z, the set of all integers. Can you form the span of all integers? That is going to be R, the span of Z.
Yeah.
You still do. So that was my question.
Sir, it is still possible. We don't have to consider the Z, right? If I just take the single element 1
Yeah.
and if I multiply
You
it,
can, but if I take the original set to be an infinite set, I still get the span.
yeah.
So now my question was, why do I need S to be finite? That was my question.
Yeah.
Okay, so
Okay.
So here, my understanding was
Yeah.
intersection of S, but that's not correct. Intersection is W.
Yeah. Intersection
So
is
in that
W.
intersection, S will
Yeah, contained in
Oh.
there. Yeah.
Are we taking linear combinations? That is why we are keeping x to be finite, because linear combination is dependent on
Linear combination is by definition finite.
Yes.
Okay, but you can choose finitely many vectors from that infinite set. And
just
make
by
linear
taking
combination.
zeros or
Yeah.
So actually, there is a thing like you can construct any vector. Like let's suppose I'm taking 2, and I can construct like 2 times 1 plus 0 times another element plus 0 times another element plus 0 times another element plus 0 times another element. So then I actually don't need that infinite vectors that is in S. That's why I don't need actually all those vectors in the first place, because what I say it like you can consider the Z and you can construct the whole real line
That
by
is the same as taking the
Just
set
one.
as just one.
Yeah.
That I agree with that.
yeah. There is a discussion on, I think it is in the
Yeah, but I think we
Yeah.
are taking too much time on this.
Yeah.
I think we should-
subsuspend by S, then any vector V of the form okay, so it is just U that is equals to C1 U1 vector plus C2 U2 vector plus dot dot Cn Un vector. Don't you think this vector belongs to W?
Yeah, because we have taken W the first place. Then the definition, the theorem you stated prior, we can speak that linear combination. Like
No.
theorem.
Can you just tell me why this linear combination, this U has to be in W?
Oh, because S of C1, U1 is in W, and then we add C2, U2, that is also in W. Then by induction, we can say, show that it is in W.
Yeah, because as you can see that all these vectors U1, U2, Un, all these vectors are in W, right? So if you add all these vectors, if you take the linear combination of all these vectors, then it still stays in the vector space W, right? So that's why all these vectors of the form U is equals to C1 U1 plus C2 U2 plus dot dot Cn Un, they are still in W. Okay. Now, and we also know that, yeah, so thus W contains the set L of all linear combinations of vector vectors in S, right? So now I am considering this set L. And what is this set? This is the set that is the all possible linear combinations of the vectors in S. Okay. So now let V, W, these are two vectors belongs to L, and then there exists U1 vector, U2 vector, UN vector belong to S, such that V vector is equals to, V will be what?
We can write it as
Linear combination, right? So V vector will be some alpha 1 U1 plus alpha 2 U2 plus alpha n UN, and then I can also write W vector is equals to beta 1 is, yeah, so S1 plus beta 2 S2 plus beta n. So where S1, S2, Sn also belong to S. Okay, so I'm considering this is M, sir. Okay. Yeah. So all these numbers, alphas and betas, they are in the field, right?
You see, Jim, my reservation is the following.
Yeah.
If you please go up.
Yeah.
Yeah, no. I think you are good. So for this span, you don't need. For this span, you don't need the set S to be finite actually.
Yeah.
Okay. But when you have S to be a finite set, then you say that these subspaces spanned by those n many vectors.
Yeah.
That is the notion of when you want to say that your vector subspace is spanned by finitely many vectors, then your set S to be a finite, needs to be a finite set. But now here in the theorem, the subspace spanned by a non-empty subset S, I think you should not start with the fact that S is a finite set. No, not there.
Okay.
In the theorem.
Okay.
In
The subset
this
spanned by
theorem-
non-empty set.
In this theorem, you're taking S to be a finite set, right?
Yeah.
I think it also true if S is an empty set. And when you're taking the linear combination, it is also automatically finitely many. So you are choosing finitely many elements from that set, and you still can prove it, I think.
Yeah.
So that was my thing.
Okay.
Like for example, like say you mentioned quadrant, then you can span the entire vector space.
Yeah, that is true.
So and in that part we have infinite number of vectors.
Yeah.
So
Okay, so sir, I think
But in that case, things will be a bit subtle because one linear combination will take m vectors, another linear combination
Exactly,
will take n vectors, and you can still do that.
Yeah.
I think that is the most general way of tackling this problem. But this is a reduced situation.
Yeah.
It's
So
a special case.
that's why, sir, I say there is a.
But it's okay to prove it. It's a hand waving way or
Yes.
a sketchy way of doing it. But
Uh,
this general case would be to take arbitrary linear combination, then you take two arbitrary linear combinations, take the linear combinations of those two.
So there is another way to define the span, and they started with like they define the span as the linear combinations. Then they show that.
Okay, yeah.
So
Yeah.
in that case, they consider first the infinite linear combination. Then they showed that there is only one unique possible.
But you see that's the problem. When you define linear combination, there is no infinite linear combination. There is a lot. You will have a lot of problems if you have infinitely many terms in the linear combination. There are many issues there. So by definition, linear combination is finitely many. But in the set, you take the span of the set. That set can be a set.
Can you state the source of the alternative?
Which one?
The one we're talking about, like say take a linear combination of the span.
Okay, so I think there is a definition in the
Can you
this.
share the source?
Yeah. Okay, I'll share that source and everything. I think there it is in the Sheldon extra. They defined the span in terms of the linear combination. Then they proved that that is actually the smallest subset of if you take the subspace. If you take the intersection of all the subspaces contains the set S. Yeah. Sir, do you say?
Yeah. I was thinking like you can choose a linear combination. I mean that. Suppose you have a subset S. I'm trying to prove it here.
Okay.
In the most general version, you have that subset S.
Yeah.
You take a linear combination.
Yeah.
That consists of m vectors. You write the linear combination, and you take another linear combination which consists of n vectors. M is not equal to n.
Mm-hmm.
Suppose you have in the first linear combination alpha 1, u1 or something like that, and for the other one w1, beta 1, and n many contributions and m many contributions. And when you take the addition of these two guys, that will be also in the linear combination, right? Because that will be a finite thing, and that will be. I think this is what you want to show.
Yeah, yes, sir. So
and that you can also do if S is infinite. That was the point.
Yeah.
Right.
So I already.
You can always write V bar as this.
Yeah.
And W bar as this.
Yeah.
Even when S is infinite.
Yeah. Right. So and then. So what you can do is you can write something CV vector plus W vector is equals to I equals to 1 to n C alpha I UI vector plus J equals to 1 to M beta J SJ. Yeah, that is exactly what I'm doing, but I started with the
look at your S. Your S was something else, right?
Yeah. Right.
Yeah, this S. I think this part can be removed, right? Yeah.
So S can be infinite.
Yeah.
So everyone understand what Syed is saying?
Sorry for the first,
No problem. So I don't need to consider a final set. I can consider it to be infinity, but still it spans the whole vector space. Okay. Okay. So from this equation, what we are seeing, what we are getting is this is actually belongs to. This is actually belongs to which? Yeah, there is this L, right? So this CV plus W is also belong to L, because these are the linear combinations of the vectors in S, right? And L is the set of linear combinations of all the L is the set of all the linear combinations of the vectors in S. So that's why this vector CV plus W, it is also in L. And from the previous theorem, we can conclude that this set L is a vector space, isn't it? Right? L is a vector space because if I prove this CV plus W form, then I know that the vectors coming from this set L is also a subspace. Yeah, right? Okay. So now, yeah. So now,
I think you could write it like N is a vector subspace.
sorry. Subspace of the vector space V, right? Okay. Now, what is the definition of span? Yeah. So first thing, W contains L and L contains this set S, right? S is the S is the set I started with. Then I construct this set L, taking all the linear combinations of the vectors of S, and this L will be a subset of the vector subspace W, right? Now, so if we recall the definition of the span, it says that S is defined to be the intersection W of all subspaces of V which contains S, right? So W is what? So just if you take Wi, then W is simply intersection I Wi, right? Right? So, and here we prove that L is a subspace of the original vector space V, and L also contains the set S, right?
W, the intersection of V or V.
No, W. So if I consider
So
Wi are all the subspaces that contains S. So what is the span of S? From the definition, we know that if you take, so what we are considering is the span of the set S, right? Span of the set S. So what is it? So if Wi, these are the subspaces that contains the set S. So every S belongs to each and every Wi. So the span is defined to be W is equals to intersection of all these Wi. Okay. And so to prove this theorem, we start, let W be the subspace spanned by S. Okay. And then we form another set L, and I show and I prove that this set L is also a subspace of the original vector space V, and this set L also contains the set S, right? So then what is the definition of span? You have to take all the intersection of all the subspaces, right? So we already know that W can be written. So it is W will be a subspace of W intersection L, right? Isn't it? Why? Because it already in this way. W contains L.
Because A is a subset of WH.
Yeah. Because you can write because
But
Yeah.
you cannot write.
sir, because W is let me write this. W is in all such intersection, because this is the definition of the span, right?
All such intersections. There is only one intersection.
No, when I'm taking the span, W will be in all such intersection.
What do you mean by all such intersections? You are taking the intersection of all WIs.
Yeah.
And you're calling that W.
Yeah. So if I intersect like W1 and W2,
The
then
intersection of all WIs, you call it W.
yeah.
Sorry,
Sorry.
is that W that defined W above?
Yeah.
See,
This is the W I started with.
yes,
Yes.
a definition.
Yeah. W is the subspace span by S. Okay.
Since we proved that L is also linear space by S, then S could be a subspace of W, right? If S is a subspace, W is a subspace, both have both vertices. So we just need to show that W is also a subset of L.
Yeah. Right. So then, and this is just what? W intersected with L. This is what? L. L, right?
But how do you write that W is containing W intersected with L?
Because that is from the definition of the span.
W is containing L.
No. Because W is the minimum set.
No,
If
if
I-
you take two arbitrary sets,
Yeah.
suppose forget about W and you take the intersection.
Yeah.
Can you write that
No,
one
no.
of the set is contained in?
No, from that perspective, I'm not writing it. I'm writing it because W is the minimum set, right? So if like W1 and W2, these are two subspaces, and if I intersect W1 with W2, then that will be W will be what? A subspace of W1 intersection W2, right?
And how about L?
L,
Is W contained in L?
yeah, because I already concluded here.
L is contained in W,
Yeah,
but not W is contained in L.
from here I'm showing that.
From where? No, when you are writing W is contained in W intersected with L, it is only possible if W is contained in L.
Yeah, that's why, because this equal.
Yeah, but how do you prove that W is contained in L? You did not show it.
No, W intersection L is L.
Explicit as W contains the set L. This is the reverse.
Right?
In the definition.
I don't know if that
All
was
linear
one.
combinations.
Did we somehow prove in last class that the intersection is the smallest element?
Yeah.
Did we prove that?
Yeah.
Then we can show that the W is the smallest span by S, right?
Yeah, that is why I am
and L
using.
is also set span by then W is a subset of L. From that argument we can conclude that and then
Yeah. I mean, if W intersection L is equals to L, and W is the smallest set, right?
yeah.
So that means W is a subset of
If W is the smallest and then L is larger than W, the set L is larger than W.
We are going to show that these two sets are equal.
I think there are two parallel arguments.
You show one inclusion.
Yeah.
Now the other inclusion needs to be proved.
Yeah. This is the other inclusion, right?
Here, if you prove it,
Sir, this is come from the argument, right?
okay.
Because W is the smallest subset. So just consider this. If I take W1 and W2.
Okay,
And-
so L contains S.
Yeah,
Okay.
definitely.
So that since W is the smallest, so W is contained in it.
Yeah.
Because L also contains
Contains
S.
sets.
Right?
That is
From that
exactly.
argument it follows that W is equal to L. Yeah.
Are you satisfied with that?
Yeah, we don't need the W intersection M.
Actually, this comes from the definition, right? This is the argument comes from the definition.
That's correct. But you don't need to go that far.
Yeah.
Please go up. So since W is the smallest one, and W is the smallest one containing S, and L also contains S.
Yes.
So W has to be contained in L. And you earlier proved that L is contained
Contained.
in W. That proves that W is equal to L.
Yeah.
Right?
Yeah.
Did you prove or you stated only?
What?
So, I mean, from that linear combination, right?
Yeah, we proved that because W contains L, right? Because all these linear combinations.
Okay, there, from that line.
Yeah.
Just one line and then it's same.
Yeah.
So that inclusion is true. Now the other inclusion comes from the fact that W is the smallest of all the sets that contains S.
Okay.
So therefore W is equal to S.
Okay. Okay. So now there is another definition. If S1, S2, Sk are subsets of a vector space V over F in the set of all sums U1 plus U2 UN UK of vectors Ui belongs to S I is called the sum of the subsets S1, S2, Sk, and is denoted by Sk. Yes. Okay. This is the sum of these subsets. And now, are you finished? Okay, so we're just taking the sum of all these subsets. Okay. So now the question is, if I'm considering W1 W2, Wk are subspaces of the vector space V, and then the notation will be W equals to summation of I equals to 1 to k Wi. Is it a subspace? So subspace. So first I define the summation, then there I consider all these sets S1, S2, Sk. These sets are subsets of the original vector space V over the field F, and the summation is defined in this way. Then if I replace all these sets by the subspace W1, W2, Wk, is this summation, this W, is it going to be a subspace?
Are W's are the subspaces containing S1, W1
No.
containing subspaces?
You just don't need to consider the sets. I'm just
Span of S.
no, you don't need to consider that. I'm just defining the summation of the subspace. Is it going to be a subspace? You have to check
It should be subspace.
Cu plus V. No, you shouldn't conclude that this is a subspace. You have to check
You have to check
if this vector belongs to W.
for any U in W and V in W.
Yeah.
And C any scalar.
If you conclude that may not be a subspace, you have to check whether it is a subspace or not, right? So so how do you check? You can consider a vector U that is belong to W. But how does W define? W is the summation of all these W1 to Wk. Then you can write U is equals to U1 plus U2 plus Uk, right? Where
These decomposition does not need to be unique, right?
yeah, for the direct sum it needs to be, and I'm going to prove that the direct sum needs to be. Ui belongs to Wi. Okay. Now for the V, you can similarly write it as a V1 plus V2 plus Vk.
I have a question.
Yeah.
Do the dimensions have to be same for all the W subspaces?
No.
So we can take like M and
Yeah. Even in which set?
Dimension is not defined.
Yes. Still, we are not considering the
Using the
dimension.
dimension.
like say the last say like say we have UK and VK. So I was asking that does the active to be
Yeah. So the thing is, I'm considering W1 and W2. It is possible that W1 contains this set U1. It can be of the form like, if I just consider an example, it can be just simply 1, but W2 can be like 1, 0. But I'm adding this, I'm not adding U1 with U2, but I'm adding U1 with V1, right?
in order to give the vector addition
Yeah.
dimension.
Okay.
So I think this addition is the addition of the original vector space.
Yeah.
Right?
Original vector, yeah, because
these are
the
all
subspace of the original vector
its
space.
class comes from the vector space V. And you
Okay.
can always do that. Because all these vectors are in the original vector
Original
space.
vector space. Right? So now what you can do is Cu plus V, and this will be what? This will be C times U1 plus U2 plus UK plus V1 plus V2 VK.
So
Right?
a small comment, like
Yeah.
when you ask this question, even before they try to answer this question, you have to define how you define this addition and scalar multiplication, right? The addition is fine. The addition in the original vector space, like you have just said, and the multiplication C times is the component-wise multiplication, right?
That is the component. Yeah, right. So
That's what you want, right?
yeah, so and it's just a multiplication by C with all these U1, U2, UK.
Yeah, it's the same multiplication in the original
Original vector space, exactly. So everything comes from the original vector space because these are the subspace of the original vector space V. So that means this is equals to summation of I equals to 1 to K and C times UI plus VI. Yeah, sorry. There should be a picture. Now CI plus VI. These are in the same.
Are these in WI?
No, they will define. They will define the term.
Because they are subspace.
Yeah. That means this forms a subspace. Right? Okay. So now let me introduce with the giving sum. Okay, so there is another theorem. Suppose U1, UM are subspaces so subspaces of the vector space V over the field F, then U1 plus UM is the smallest subspace of V containing U1 UF. Okay. So how can you prove that? So first of all, you need to show that it is a subspace, and it is a subspace because we already proved it here, right? In here we proved that this summation is a subspace. Okay. Now all these u1 dot dot um is contained in this summation right? Isn't it? All these u1, u2, all this subspace contained in this summation. How is that?
Right.
No, just you can give a simple example, right?
If UV contains U subspace, then U plus V is contains subspace.
No, actually, if you consider it like the, let's say, R3, this will be what?
RLI could be.
And if you consider everything as R, and R, and you decompose this, actually, I'm not even defining that, but a simple example, you can consider all the other elements 0, u2 to um, all this to be 0. Like you can, if x vector belong to u1, and if you take 0 vector belongs to ui such that I is greater or equal to, then x vector plus 0 vector plus 0 vector plus 0 vector, this is an element of u1, right? So that means u1 contained in this, isn't it? So that means every other u2, u3, everything contains in this summation, right? Okay. So conversely, every subspace of V containing u1, contains right? Sorry, isn't it? So if you take a subspace that contains all these subspace u1, u2, then it is definitely contains u1 plus u2 plus dot dot u.
Each of these, right?
Yeah. No, sir. It has to contain all of these.
Yeah, that means that
Yeah.
you are containing each of these. When you say just contain, it means that it contains any of these.
Yeah. Each of these, right? That means the summation, it is the smallest subspace of V containing all this. So this is thus u1 plus u2 plus is the smallest subspace of V containing u1 dot dot right? Okay, so now let us define the direct sum. So from all this discussion, what we can say is, suppose u1 dot dot um are subspaces of V. Every element,
Excuse me.
yeah,
So here the search shouldn't be right containing each of these U1 dot dot.
So
is
you
one
write
subspace
each
of
of-
whatever.
Each of these.
Yeah.
Sorry, this subspace of V, every element of u1 plus u2 um can be written in the form u1 plus u2 plus um, right? Where uj belongs to uj. Now we are actually interested in the case where each vectors in u1 plus u2 plus um can be represented in the form above in only one way. So this situation is so important that it has a special name. It is called the direct sum, and we're going to define the direct sum now.
Idiots.
Yeah, direct sum. So we are interested of each vector in this. So what Sir is saying a few moments ago that it is not unique. This representation is not unique. It can be. It is possible to express these vectors in a different way. Okay, but here we are interested in a unique way of representing a single vector. Okay, so the definition. And these definitions, direct sum. Suppose u1, um are subspaces of a vector space V over the field F. The sum u1 plus um is called a direct sum if each element of u1 can be represented in only one way as a sum u1 plus un, where each uj belongs to uj.
I think you can put a vector.
Yeah.
U1 vector.
Right. Okay. The second condition is if u1 plus um is a direct sum, then u1 denotes un with the notation serving as an indication that this is a direct sum. So this is the definition of the direct sum. Okay, so what we are considering is here, this is important. So can be represented in only one way. So we are not considering any other way. We are considering just a unique way to represent a vector in this form. Okay, and for the notation, we are considering this for the notation of direct sum. When I write something like this, it means there is only one representation of this form. Okay. Yeah.
Here, so for each uj,
Yeah. uj belongs to the subspace.
Now it comes to cross correction because we have Wi-Fi finally. So the network is Tensor. The Oxford is Tensor College guest. When we do T is that whole.
so here the capital U on the right side is not a vector.
No. Capital U are the vector subspace of the original vector space V. So I started with these are the subspaces of the
These are
vector
capital.
space V. Yeah. That's why I put a vector symbol on these vectors. There is no vector symbol in the subspace. Yeah.
The example you gave us, let's say in R3, you did R1s. Let's say they had only one intersecting element, that is the 0.
Yeah.
If they have many more intersecting elements, that can be writing as a direct sum.
Yeah. So I'll prove that why this is going to be okay. So
So there is no symbol for subspace.
no symbol for subspace.
So we don't put anything.
Not actually, because that is a vector space.
So just put
It
a
is.
capital letter.
Yeah. Yeah, we can consider something, but there is
But
not
there is
a
no restriction.
yeah popular convention. So now let us define it. So condition for a direct sum, suppose u1 dot dot um. These are the subspaces of the original vector space. Subspaces of V over F. Then u1 plus um is a direct sum.
So is it from Hoffman and Woods?
No, it is not from
So it's fine here.
over F. Then this is a direct sum if and only if the only way to write 0 is a vector here as a sum u1 plus um, where each uj is in uj. Yeah, sorry. Each uj is in uj is by taking each uj equal to 0. Yeah. So this is the condition. So if all these are the subspaces of the vector space V over F, then the summation is a direct sum if and only if the only way to write this vector 0 as a summation of this, you have to take all these uj to be 0. Okay. So the first, so it is a if and only if statement, right? So we have to prove this in the both ways. So first, suppose u1 plus um is a direct sum. Then the definition of the direct sum is what? So from the definition, it says that the sum is called a direct sum if and only element of this can be represented in only one way. That is the definition, right? So now if I take this to be a direct sum, then it is immediate that 0 can be represented in only one way, and you have to consider all the summation of all the zeros. So
You can
0
use
will
that
be,
symbol.
yeah,
Use that symbol here. Can use.
yeah.
That's happening.
So for the direct sum, I'm considering I want to prove that this is a direct sum,
Okay.
right? So this, yeah, it is not proven yet. So since I'm taking this to be a direct sum, and from the definition it says that there is only one way to express vector, and then 0 vector will be what? zero vector can be represented in only one way, and that will be zero vector plus zero vector.
It has to be unique. Is it necessary that it has to be zero? Sum of zero vectors.
I don't understand the question.
The condition is that the sum should be a unique sum, right?
Yeah.
But not necessarily all of them has to be zero. Is it?
Yeah, it has to be zero, because otherwise you cannot prove that this is zero, right? Only one representation for zero. Unique representation when we are considering the direct sum. So if you take like zero vector and you write something like 0 plus u2 plus dot dot sum u3, then it violates the definition, because then 0 can be expressed in this way and in this way, but that is not the definition of the direct sum, right?
Alright, yes.
Right? Okay, so if we consider the definition, then it is immediate that this is a direct sum. Okay, now suppose so I'm proving it on the other direction. So now suppose that the only way to write 0 as a sum u1 vector um vector where each uj belongs to uj is by taking yeah where each uj belongs is by taking each uj equal to 0. Now we want to show, so
Isn't it supposed to be zero vector?
yeah, we want to show that u1 plus u2 um is a direct sum. So if I consider a vector belongs to in this vector space, in this subspace, okay, so right so I'm considering v is a vector belongs to u1 plus u2 plus u. Now v can be written as yeah u1 plus um, all these are vectors for some u1 belongs to u1, um belongs to um, so to show that this representation is unique, let us consider that there is another representation of v and that can be written as v1 plus v2 plus vm, where each of these v1 belongs to u1 and vm belongs to u1. Now these are the same vector, right? This v, I can subtract one from another. Then the left hand side will be what? The left hand side will be 0 vector, because this is a v vector and this is a v vector. Then the left hand side will be 0 vector, and 0 vector equal to u1 vector minus v1 vector plus u2 vector minus v2 vector plus m vector minus vm vector, right? So but now suppose that the only way to write 0 as a sum at the where each uj is by taking this is equal to 0, right? That means each of these will be what? Each of these will be 0. Then
you have to invoke the condition that u1 is in the subspace with u1.
yes, sir, I
u1
already did.
vector is also in the subspace
u1.
u1, so it's whole thing. u1 minus v1 is also in the subspace because that's a subspace.
Yeah, right. So
And all these things in the bracket belong to the respective subspace.
yeah, so this is a case u1 and this. So all these things like u1 minus v1, this vector belongs to what? u1, right? I think I put a vector symbol here. So that means the subtraction makes sense. That means you can write u1 vector minus v1 vector. This will be 0. That means u1 vector equals to v1 vector. In general, this is ui minus vi equals to 0. That means ui equals to vi vector. That means there is yeah. That means for each of these cases, this is what? This is a unique representation. So u1 equals to v1. That means the representation is unique. So the condition is proved, right? Okay. Finally, there is only another theorem. Yeah. How long? So we'll take another 10 minutes. Yeah. Direct sum. Suppose U and W are subspaces of V over the field F, then U plus W is a direct sum if and only if U intersection W is equals to the 0 vector. So we need to check if u intersection w is equals to the only 0 vector, then the summation u plus w, this will be a direct sum. Okay. Yeah.
This is vector.
Yeah, this is 0 vector. Yeah.
It's a theorem.
Yeah, it's a theorem.
This U or V? Oh, so U.
U
and W
intersection-
is a V or a,
Yeah.
then U plus W, right?
Yeah.
These are all subspaces.
Yeah, u and w are subspaces of the alternative space V over the field F. Then u plus w is a direct sum if and only u intersection w is the only 0 vector. So the proof is first suppose that this is a direct sum. First, that u plus w is a direct sum. If v vector belongs to u intersection w, then 0 equals to what? 0 vector equals to v vector plus minus v vector.
There's V, UV, UV contains
Yeah, which one you are talking? So this is a v vector
process.
that belongs to u intersection w. Then I can write the 0 vector as v plus minus v vector, right? So from the definition of the direct sum, we see that v belongs to the vector set u and minus v belongs to w. Yes, because I started with this is the definition of the direct sum, right? So I consider this is a direct sum. So of course every vector in this vector space u plus w, it has to be in this form, and from this the sum is called a direct sum if each element of this for u1 plus um where each uj belongs to uj. You see? So u1 belongs to which vector subspace? u1, and um belongs to this subspace um, right? And then 0 is equals to v plus minus v vector. So v vector belongs to u. Yeah.
I agree with him. How we show that v vector is in u and minus v vector is in w actually follows from the fact that v vector is taken to be in the intersection. So that's assumed that v is
Yeah.
in the intersection.
Yeah.
And from which it follows that v is in both the subspaces.
Yeah.
And hence v is both in u and w.
W.
So which means that v is in u. Okay? And now since v is also in w,
W.
minus v is also in w because w is a subspace.
Right?
So v vector is in u and minus v vector is in w. And 0 has this decomposition, which probably contradicts with the fact that
Right?
that 0 can have only that decomposition.
Yeah.
0 plus 0.
Yeah. So what Sir is saying is, by the unique representation of 0 as a sum of the vector in U and vector in W, we have V equal to 0. It has to be V equal to 0, otherwise it is not a direct sum, right?
So this contradiction proves that non-trivial vector V vector
Cannot be.
in U intersection V is not possible. That is invalid. Right? The only vector can
Is not possible.
So I think
Yeah. So
if you want to write it like that, you should write that.
yeah, okay, sir.
Non-zero.
Yeah.
So you start with non-zero
For a
vector.
non-zero V vector belongs to U intersection W. That means what? V belongs to U and V also belongs to W. And since these U and W are subspaces, that means minus V also belong to U and minus V also belong to W, right? But so 0 can be represented as 0 V vector plus minus V vector, right? But the unique, so from the previous theorem, you know that there is only one representation of 0. And if it is a direct sum, then there is also another representation of 0 vector, that is 0 vector plus 0 vector. So these two contradicts the definition of the direct sum, right?
If V vector is non-zero,
Yeah.
then they contradict.
If V vector is a non-zero vector, then these two statements contradicts each other, contradicts the definition of the direct sum. That means V has to be equals to 0. Otherwise, this is not a direct sum. Right? Okay. So the other way proof is now let U intersection W is the 0 vector. Now suppose U belongs to U and W belongs to W, and let 0 vector equals to U vector plus W vector. Okay. So so from this equation, what I can write is U vector equals to what? Minus W vector, right? Right? That means minus W is what? The additive inverse of U. Sorry, U is equals to minus W, sorry. Then, and this is belongs to which vector space W? Because W is a subspace. So if W vector belongs to W, then minus W also belong to W, right? But so thus U vector belongs to what? U intersection W. I mean, also U vector belongs to W, that means U vector belongs to U intersection W. Yeah, in the both. But we started with that the intersection only contains the 0 vector. That means u equal to what? 0 vector, right? So u equals to 0 vector. That means w vector is also equal to 0 vector, and 0 vector is equals to 0 vector plus 0 vector, the unique representation, right? That means this u plus w is what? Is the direction. That means you can write it as,
So
yeah,
when we put that this is the direction, we are using that the result that
Yeah,
we
from the
put
previous
earlier,
theorem.
that
0 has only
direction
one.
is equivalent to the fact that 0 vector has the unity component.
Yeah, right.
0 vector, but you are not using the definition of the direction
No,
to do that. You are
Yeah.
using that previous
yeah,
result.
previous test.
So finally, is it M?
Yeah,
The-
sorry, this is it. Okay.
Okay, so when we write, can we write R2 as R direction R? Can we write this R2 is equal to R direction R. So there is the point 1 in R in both R, but they are supposed to contain only 0 to be the common element, but 1 is in both R's.
So
How can that be a direction? It's a question for you.
Yeah. So what Sir is saying? 1 belongs to R, and if you consider this, and also 1 belongs to this one, right?
Does it contradict the definition?
So because from the direct sum definition, we know that it has to be, the common element should be just 0. Yeah. Which one?
Isn't it supposed to be each element from R set of real numbers? If it's 1 and there is 0.
No, it is not. Yeah. So how many are? So
I think she tries to say that, if I understood her correctly, that these two ones are different ones.
right.
Probably has what she means, right? She's correct. At a glance, it seems that they are the same one, but they are not the same one. One is 0, 1, and the other one is 1, 0.
So actually, this is R2 is a generic element of R2 is what? X, y belongs to R2, and this R actually X, 0, and this R is actually 0, y, right? So this is the element of 1 belongs to R, and this is the element. So both these are in R, but the
It's
intersection
not writing that
R. Yeah.
like some Tudor or something like the double Tudor, which is isomorphic.
Yeah, asymmetric R.
As you vary x in the real line, that x,